Hello, I'm Professor von Schmohawk, and welcome to YU. For the last several lectures, we have studied systems of linear equations in 2 or 3 variables, and we have seen how these systems correspond to lines in the Cartesian plane or planes in Cartesian space. This connection between algebra and geometry was proposed in 1637 by René Descartes in his book La Géométrie. Since our brains come pre-wired to visualize objects in 3 dimensions, visualizing equations as geometric objects can often give us insights into the underlying mechanisms behind algebraic procedures. Geometric visualization is especially useful in understanding systems of equations. We looked at systems of equations in 2 variables geometrically in the lecture Why the Elimination Method Works to gain insight into what happens during the process of variable elimination. In that lecture, we saw that when 2 equations which share a common solution are added, the resulting equation will also share the same solution. Therefore, when 2 equations for lines which intersect at a point are added, the line corresponding to the resulting equation will also include that point. By multiplying one or both equations by constants before adding, the resulting line can be rotated into any orientation around the intersection point, depending upon the constants that are chosen. So when we choose constants which cause a variable to be eliminated, we are actually choosing constants which cause the resulting line to be rotated to either a horizontal or vertical position. The resulting equation then tells us the value of the x-coordinate or y-coordinate of the intersection point, and thus the common solution of the equations. In this lecture, we will show that this same principle applies when adding linear equations in 3 variables. The difference is that instead of adding equations which describe lines, we are adding equations which describe planes. Just as with lines, the intersection of 2 planes represents the equation's common solutions. And when those equations are added, the resulting equation will also share those solutions. Therefore, when adding equations for planes which intersect along a line, the new plane corresponding to the resulting equation must also include that line. As we did with equations for lines, we can prove that this will always happen by showing that this is true in a general case. When 2 equations are simultaneously graphed, any point where the graphs intersect is a point where both equations are satisfied. The line of intersection of 2 planes thus represents all the points where the plane's equations are both satisfied. Let's call these 2 equations Equation A and Equation B. And let's call the expressions on either side of these equations expressions A1 and A2 and B1 and B2. Now let's add equations A and B to produce a new equation. Since the intersection of the graphs represents all the points at which equations A and B are both satisfied, at every point on the line of intersection, expressions A1 and A2 have the same value, and expressions B1 and B2 have the same value. So at every point on this line, both sides of the resulting equation have the same value, and that equation will also be satisfied. Since the resulting equation is satisfied along the line of intersection, its graph must include that line. Therefore, the resulting plane will always pass through the same intersection line as the original 2 planes. Additionally, as we saw in 2 variable systems, multiplying one or both equations by constants before adding can change the orientation of the resulting plane. although it must still include this line of intersection. Depending upon the values of the multipliers we choose for the equations, the resulting plane can be oriented in any way around the line of intersection. We know that in the elimination method, the values of the constants are chosen so that a variable is eliminated from the resulting equation. So what does this process look like when viewed geometrically? To understand, let's first see what happens when we eliminate a variable in the equation for a line. If we start with a linear equation in x and y and eliminate x, the graph of the resulting equation will be parallel to the x-axis. Likewise, the graph of an equation with y eliminated will be parallel to the y-axis. The same holds true for linear equations in 3 variables. The graph of an equation will always be parallel to the axis for the variable which was eliminated. As an example, let's start with the equation x plus y plus z equals 3. The graph of this equation intersects the x, y, and z axes, so it is not parallel to any axis. If we like, we can find the point where this plane intersects an axis by setting the variables corresponding to the other axes to 0. For example, to find the z-intercept of this graph, if we set x and y to 0, we see that the value of z must be 3. So the plane's z-intercept is 3. On the other hand, the plane corresponding to an equation which does not contain the variable z will be parallel to the z-axis. The plane will either contain the z-axis or have no z-intercept. For example, if we eliminate z from this equation, we get the equation x plus y equals 3. This plane has no z-intercept. Since this plane never intersects the z-axis, it is parallel to that axis. Likewise, the graph of the equation with y eliminated will be parallel to the y-axis, and the graph of the equation with x eliminated will be parallel to the x-axis. So we have seen that when equations for 2 intersecting planes are added, the resulting plane must include their line of intersection, and if in this process a variable is eliminated, the plane must be oriented so that it is parallel to the axis for that variable. No matter which way the line of intersection is positioned, the resulting plane can always be oriented parallel to any given axis. To illustrate how the resulting plane can be oriented parallel to any axis, regardless of the position of the line of intersection, let's start with a case where the intersection line passes through the origin. Remember that the orientation of the resulting plane is determined by the multipliers we choose when eliminating a variable. And by choosing appropriate multipliers, it is possible to orient the plane any way we like around the line of intersection. Rotating the plane around that line, we can see that it is always possible to orient the plane so that it includes the x-axis, the y-axis, or the z-axis. Likewise, when the line of intersection does not pass through the origin, there will always be an orientation where the plane is parallel to the x-axis, y-axis, or z-axis. So in adding equations for two intersecting planes, by choosing appropriate multipliers, the resulting plane can be rotated into any position around the line of intersection. And since it can be oriented parallel to any of the three axes, we can see graphically why any variable can be eliminated from the resulting equation. Looking at variable elimination geometrically, we can also see why in the last lecture we found that no matter which pair of equations we use to eliminate a given variable from a system of three planes which intersect along a line, we always ended up with the same equation. In that lecture, we found that eliminating x always produced the equation y plus z equals 1. No matter which pair of equations were used, we always ended up with this same equation. Likewise, eliminating y always produced the equation 3x minus 4z equals 10. And eliminating z, we always got 3x plus 4y equals 14. Looking at this process geometrically, it is now apparent why when all the planes pass through the same line of intersection, eliminating a given variable always produces the same result. Since all three planes pass through the same line, no matter which two planes are used to eliminate x, the resulting plane must pass through this line and be oriented parallel to the x-axis. Since there is only one possible way in which a plane can be oriented to simultaneously pass through the intersection line of the three planes and be parallel to the x-axis, we will always get the same result when we eliminate x. Likewise, any pair of equations produces the same result when eliminating y or z. When we first introduced systems of linear equations, we initially studied systems of two linear equations in two variables. And we saw how these systems could be used to model and solve real-world problems. In the next lecture, we will see what kind of real-world problems systems of three linear equations in three variables can be used to solve.